Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Introduce Andy Bagel, who is visiting us from Berkeley. As some of you may know, there's a new research effort within Microsoft Research looking at basically the intersection of HCI-style research and software engineering. So we're interested in studying programmers as users, and Andy fits right into that mold. Today he's going to talk to us about what it might be like to enter programs via voice instead of keyboard. And he assures me that that is often a contentious topic and welcomes you to interrupt for questions and feedback throughout the talk. But we won't hassle him too much. Anyway, thanks, Andy.
Thanks very much. All right, so what I'm going to talk to you today is about my dissertation work at Berkeley. I'm finishing up this year, hopefully this summer. And it's programming by voice. And okay.
There we go.
Oh, wow, even I can hear that. All right, well, I can introduce myself again. I'm Andy Bagel for all the people watching from home. And I work in interactive software development. So let me motivate what I'm talking about today, which is programming by voice. So conventionally, most programmers use the keyboard. They program for long hours and are thus at risk for getting repetitive strain injuries or carpal tunnel problems with their hands. And if you think about it, if you're a programmer and your keyboarding is your lifestyle and you get RSI, you're kind of out of a job. So it might be time to look for something new, except what we are doing is trying to find an alternative. So we asked the question, can you use speech as an alternative for typing in the programming task? And what's interesting about that is that it takes speech, which is a very inherently ambiguous domain, which is spoken English, and combines it with something that's completely unambiguous, programming languages. In fact, mathematically precise. They have to be exact, and programmers understand that. So what we found is that this is also a really interesting area to study ambiguity mediation, something that Jennifer Mankoff at Georgia Tech worked on. So what the general goal is with all sort of human-centered research, you first look at your users. You look at your programmers and you say, well, if you could speak code, what would you say? And find out how they would verbalize the code, what kinds of things they need to do in order to read the code out loud, and then use this to help develop some input form that the computer can understand. Then what we do is we build a development environment that works with this new input form. And it turns out that it requires quite a bit of program analysis in order to understand it, and I'll explain why. And finally, what we do is we then test it with the developers to make sure that our design is interesting, it could work, and try to iterate and figure out some better ways to do things that once we figure out whether it works or not. So there are 4 challenges in this research. The first, programming languages are not designed to be spoken. Programming is a written activity. It's on a written medium, and it's never really been spoken before. So taking this to a verbal medium is sort of a challenge. Speech is ambiguous. Programming languages are not. So this means that you're going to have to somehow figure out what the human intended to program onto the computer when you are transcribing the code. Thirdly, speech tools that come with commercial speech recognition from those vendors is actually really poorly suited for code. And I'll explain why sort of towards the end of the talk. And finally, programmers obviously aren't used to verbal software development because, well, they've never really had a chance to do it before. So this is something that we'll have to work. This is sort of a training issue, if you will. Now, in the talk, I'm just going to go through a bunch of things. I'm going to start now just sort of illustrating what I really mean by programming by voice. So let's say we've got a for loop on the screen, and I'm trying to count from 0 to 9, and I want to do it by voice. So let's take what you have to do if you are using the current state of the art, which is called voice code, which comes from Alain Desilets in National Research Council in Canada. So here we've got a person saying for loop, which introduces a code snippet, something very familiar to you guys. Then we say after left paren to move the cursor over to the first hole in the template. Then we say declare India of type integer. So in most voice recognition tools, you use the military alphabet to spell words, especially single syllable words like I, to make sure that you get them right. In this language, you say the type of the variable after you say the name of the variable. And then we say assign 0, not equal 0, because in this language you have to say assign. So there's sort of a custom vocabulary that you have to learn. And then say after semi to move the cursor over to the next template. Then we say recall 1. Now what's interesting about this, if you look on the left, there's something called a cache pad. Because it's difficult to say identifiers, in most cases identifiers are a lot longer series of words, every time you say an identifier, it gets dumped into this cache pad, and then you can reference it by number instead of by name. And number recognition in voice recognizers is fantastic, as opposed to arbitrary words or sequences of words. So we say recall 1 to grab the I out of the cache pad, and then we say less than 10, and then after semi to move to the next piece of the code template, and then recall 1 again to get the I, and then increment, not plus plus, because again in this language you say increment, and then say after left brace to move into the body of the for loop. Now, at this point, we run into one more problem, which is that after the template is filled in, it's gone. So forever after, our editing is now based on text. Move forward 5 characters, move back 10 characters. There's no concept of these chunks anymore. So in the space of programming by voice, there's been a bunch of work for people trying to develop these systems, and I've put them on 2 different axes. So let's take the left axis. This is basically how many tasks in software development, how many tasks in sort of software programming does the tool support. Now, most tools actually only support authoring. You can write the code, but once you get it into your editor, you're pretty much then on your own editing text. Some tools, very few, actually support multiple tasks like navigation and editing. None of these tools support tasks outside of the scope of what you do with your editor. Now, on the bottom axis, we have whether the tool is computer-centric or human-centric. And computer-centric means that the human adapts to the way the computer wants you to speak. So like something like graffiti on a Palm Pilot. You need to learn how to use graffiti in order for the handwriting recognition to work. By contrast, we've got human-centric, which is a means where the computer is trying to figure out what you want to say. And obviously there's a continuum here. I kind of vote for solutions on the side of human-centric solutions. Now, we've got all this related work. Actually, 2 of them I can take away because they never actually were implemented. They were just designs. And actually, of course, where I want to be is at the top right, where you always want to be in a graph. A human-centric solution that solves multiple tasks, navigation and editing, as well as code authoring. Now, what we did to start is we did the study to find out how 10 Java programmers, 10 expert programmers would speak code if they were handed a page of code out loud and told specifically you are driving a person at the keyboard, a sophomore in computer science who's taken Java but does not know anything about what you're trying to code. And read this code out loud as if you were doing that. And I tape recorded it, and then I analyzed the results. So this is actually being published in VLHCC in September. So the first thing we found out, which was very, one of those thank goodness moments, pretty much everybody speaks the same way, which is, was not a given when I first started this research, because there's absolutely nothing in the literature that says everybody knows how to say code out loud. So what did people say? Well, here's our for loop. What people said was for int I equals 0, I less than 10, I plus plus. They said the natural language words that you see on the screen. They did not say the parentheses. They did not say the semicolons. They they didn't say the braces. They didn't say, they said plus plus, so they kind of separated those two tokens, that token over here. They did not say a few other things, which I'll get to, which is a problem. But for the most part, you guys listening to for int I equals 0, I less than 10, I plus plus, you all figured out that was a for loop. I wouldn't even have had to show that on the screen. But there's actually a problem. Let's say we want to actually have a computer understand this. Whoop. Yes?
Anybody actually say I gets 0 rather than I equals 0?
I sometimes say it. I didn't see any of the 10 say it. So, nobody said semicolon in this case. Yeah.
And nobody said things like for I going from 0 to 9.
One person said for I from 1 to 10, actually. And he was an expert programmer, which is good. It's very close. So, there.
Speaking with a Pascal accent.
Yes. That's good. So there were some weird things that people said that I want to go over. So how would you say the first construct on the screen there? Cast foo int. Anyone else?
Foo as int.
Foo as int. Everyone said the word foo before the word int. That's exactly what most programmers said, except they had this problem because they were reading the code. So they said cast something to integer. That something is foo. Because they needed to say something for the sentence structure, but they didn't actually see the word foo yet because they were reading the word int. So there was a little awkwardness if you, with the structure of English. Now, the second one, how would you say that one out loud?
Well, it could also be an awkwardness in the syntax of C.
It could be the awkwardness of the syntax of C or Java as well.
I think of it as more natural to say foo and then say what the signature of foo is, but you're not allowed to write that in C.
Exactly. So there's been mismatches with the way that you think with the way that the programming language wants you to write it down.
Oh, yes, indeed.
Anyone have an idea for the next one?
So I would say 3 plus 5 times 7.
Okay.
3 plus 5, then times 7.
Then times 7.
Actually, I would say open paren 3 plus 5 close paren times 7.
Okay, so 3 different ways to say this. Some people also said 3 plus 5 quantity times 7. So in a bunch of the cases, they mentioned the closed paren, but didn't mention the open paren. In some cases, they use pausing, and I'll get to that because that's actually really interesting. There were some other problems with what people said. Most of the time, they didn't say the dot in system.out.println. Sometimes they did. I had it like 5 times in the page of code, and they would say it different ways every single time. There were lots of different ways to say an array reference. So bar sub I, bar of I, or particularly a good one usually from people from India said I from bar. I thought that was interesting. Non-native English speakers and English speakers said things very differently also. So non-native English speakers almost never pronounced ter as ter. They always spelled it out. So partial words were always spelled out by non-native English speakers. Same thing for print line. I know that's an abbreviation. I know where the word boundaries are, but a non-native English speaker usually said print ln. Finally, the last one is actually an issue in prosody. So the difference between these two to a native English speaker is array sub I++ and array sub I++, where there's a pause in between different places in the code. A non-native English speaker, when encountering this ambiguity, usually said, take the ith element of array and add 1 to it. Not necessarily. It's a little less ambiguous. And actually, that actually helps us quite a bit because with our commercial speech recognition tools, we don't get any timing information. We certainly don't get any pitch information. All we get is the words that people said. So having these alternative phrasings for these words allows us to sort of support both more developers as well as actually handling these kinds of ambiguous situations where a native English speaker wouldn't have thought that there would be an ambiguity.
I type a lot with my hands and therefore I end up with RSI. But biologically, are humans made to talk the whole day, or am I going to have the verbal equivalent of RSI if I do programming with my mouth?
So the verbal equivalent is called voice strain?
Voice
strain.
Great.
Voice strain, yeah. So like repetitive strain injury, so voice strain. That's a problem for people who are new to voice recognition. Usually, if you're going to be using voice recognition for a long period of time, you undergo a training period where they teach you both how to speak quietly and take frequent breaks, essentially, not talk very often. So it's the same thing kind of for coding. Like, you don't really code constantly typing for 8 hours a day. You kind of get up every so often. At least you have to go to the bathroom. You kind of get up and like look at your email when it comes in. You type your instant messages. So you're not always doing the coding, which actually is sort of very similar to studies of how people do write code.
How severe can voice strain get?
Voice strain will make you hoarse and not be able to talk for like a day. It's like laryngitis. And that could be a problem. So what we did after we did this study is we took that information and we used it to design a new variant of Java that we call spoken Java, which is what we hope is a more natural way to code than the voice code environment. So we've got our for loop, and we want people to say for int I equals 0, I less than 10, I plus plus. Now, when we have a computer understand this, we run into some more problems. Well, because what I just said actually could be interpreted as for int I equals 0, I less than 10, I plus plus. Nobody said how to spell any of those words. Is for a keyword or a number? How do you spell I? And is then a keyword or identifier, depending on how I spell it. It changes the meaning. But of course, oh, well, I'm a human. I could eyeball that. That's easy enough. But what about this one? So how would I say that out loud? OK, well, 4 times equals 8, file to load times equals 1. OK, but that could be interpreted as 4 times equals 8, file to load times equals 1. Or 4 times equals 8, file to load equals 1. So the same verbal utterance can come out with lots of different interpretations. So the real question is, how do you fix that? And how do you get rid of that? And the answer is to use the program context. And throughout the talk, I'll show how that works.
Is that any different from natural speech recognition? I mean, you have the same problem and you use sentence structures and stuff like that.
In natural speech recognition, they used to try to use grammars and semantic analysis to understand everything. Quickly realized that, one, the grammar for English was like a bazillion productions, and that they didn't understand what people were talking about anyway, so they couldn't figure out which words that they really did mean.
Well, I didn't really mean sort of grammar-based, but sort of, you do have a learning phase, and these tokens appear next to each other more often.
So that's a statistical learning approach, which is what they usually do now for English. One of the advantages of programming over a natural language is that we actually understand completely the semantic analysis domain. We understand exactly the program that you're writing because a compiler eventually has to understand it. So if you're writing in a program that already exists, which is the typical for programmers, you can actually completely constrain what the interpretations could be. So there's a design trade-off between the language we understand, which is this language a command language or is this a natural language? Now, if this is a command language, it's much more like insert a for loop. It's going to have a variable, name that variable I, and you're going to have very specific commands for putting in pieces of that for loop. And it turns out that command languages are really easy to analyze because they're very constrained, but the problem is that they're very constrained and they're very difficult to learn. Natural languages is obviously really hard. Like if I wanted to say, count from 1 to 10, I can think of at least 50 different ways to say count from 1 to 10, including count from 0 to 9, if I'm being really picky. Especially if the computer language is supposed to figure out that I really mean count from 0 and put 10 in the second slot and not 9. So natural languages are really flexible, but obviously very ambiguous. So the trade-off where we want to be is somewhere in the middle, something that's actually easy to say but analyzable by a computer. So what we built is this spoken Java. It's semantically identical to Java because when we try to help programmers, we don't get to dictate what their code is at the end of the day. At the end of the day, it's their boss who says, you shall program in C++. Now, it's our job to sort of make it easier for them to get the C++ into the computer, but not to say you need to program in our whiz-bang new programming language that we've just made up special for voice. So spoken Java is syntactically easier to say than Java, and the kind of methodology we used is generalizable to other programming languages. To give a little illustration of a high-level overview of what it is, all punctuation has English equivalents, and open brace. Some of them are context sensitive, like end the for loop or end the class. That's what most people said. Punctuation is all optional, completely and utterly. You don't have to say it. There's verbalizations for every abbreviation in the language, and every abbreviation that you'll find in the API. It's kind of a general support for abbreviations in general. And also, we've modified some of the productions to be a little bit easier to say in English, such as the cast operator, where you can say cast foo to integer instead of the other way around. You can say assignment with assign foo to 6, foo gets 6, set foo to 6, and also this array dereference operation. Yeah?
I think there are a lot more number of programmers in C++ compared to Java. Why did you guys choose Java as opposed to C++?
Java is smaller, easier to analyze, and for a dissertation project is tractable. So it's not a question of, we don't like C++ or we don't feel it's a relevant problem. It's more that I only had so many years to do it.
I mean, can you give me an example of an analysis which you can do for Java, which you will not be able to do for C++?
I might be able to, but I would, let me think about it for a little while. I'll talk to you after.
Okay.
So what we do with this programming language is we put it into an editor. So we have our editor is called Speed. It supports this naturally verbalized input form. Speed stands for speech editor and is also catchy. We use off-the-shelf commercial speech recognizer. Originally we used IBM ViaVoice, but we're thinking about switching to Dragon, naturally speaking. We stick our programming environment into Eclipse because it's not really fun to write an editor over again. And we use a lot of analysis infrastructure that comes from the Harmonia research project, which we'll talk about next. So we've got spoken Java language for composition. We've got a spoken command language for dealing with editing, navigation, template instantiation, transformations, search. And we want to incorporate some audible and visual feedback to handle the problems where when you're speaking, you generally have problems with your, you have less capacity in your short-term memory, something that Ben Schneiderman kind of figured out. And if you were at his talk yesterday, he might have said something like that. So by incorporating some visual feedback, you help remind the user what they're about to say. Audible feedback helps train the user on what's allowed to be said. So you can highlight something and say, how do you say this out loud? So that's similar to a JavaSpeak project at Winona State University. So Harmonia is a project I worked on since I started in graduate school. It's sort of a program analysis infrastructure designed for incremental, for interactive programming tools. And so a lot of the analyses are incremental. It's got your favorite lexer, parser, semantic analysis. And it supports a whole bunch of different languages. We don't do C++ yet, which is another reason why we didn't do C++ here. C, actually, Steve in the audience actually did our C implementation, which is very cool. And Java Titanium, which is a parallel superset of Java. Cool. We can also handle languages where whitespace is important, such as like your Pythons. We do Flex and Bison because those are important for language designers. Harmonia also does interactive program transformations. CodeLink is a way to manage your code when it's duplicated and you can't abstract it into a function or you just don't want to. And shorthand editing, I'll talk about a little bit later, who's also originally conceived of by this guy JJ, who's also an intern here at Microsoft. It seems that everybody is coming to Microsoft. So maybe that means something. OK, so let's tell you how it works. A traditional compiler consists of 3 pieces, at least the front end of a compiler, which is lexical analysis, where you take characters and you turn them into words. Parsing, where you take those words and turn them into program structures. And then semantic analysis, where you actually figure out what those words mean, and you do name resolution, names and uses and definitions, and you also do type checking and figure out whether the program is correct. So all this works for unambiguous programming languages, where you know exactly what the user typed in. Now, what we've done is extended it to support ambiguities that come from human speech. So first, we take our lexical analysis and we make it support homophones, think words that sound alike but are spelled differently that come in from human speech. We have an ambiguous parsing algorithm, which is able to take those homophones and also much more ambiguous grammar for Java and turn that into possible program structures. And then we use semantic analysis to help figure out which of those possible structures, possible interpretations are legal and get rid of the illegal ones. So just a little more in detail, we use a commercial speech recognizer. We pass it through a homophone dictionary that I snarfed off the web that has really cool homophones. Some of them are dialectical. So like if you're from New York and you say draw, D-R-A-W-E-R, that's a synonym for draw. I like that.
What's a homophone dictionary?
A homophone dictionary is you basically look up a word and it tells you all the words that sound alike. And then we run it through our lexer to figure out what those words mean. Now, some of the problems that you can get with the analysis are if you say for I equals, well, that actually could mean lots of different things. 4 could be spelled 4 different ways. I didn't say how to spell it, and equals could also be equals equals, and you just didn't say double equals. And you could have the spelled out word, or you can have the symbol. Now, in addition to the fact that you can have different spellings, I also didn't tell you where the word boundaries go. So I could have for I as just a single identifier. I could have the whole thing be one gigantic word. I could have also, actually, I didn't tell you where the capitals were, capital letters. I didn't tell you where the abbreviations were. You know, there's all the sorts of things that are lexical in nature that don't come out from human voice, that do affect a compiler. So once we get all those possibilities, we pass them all on to our parser. And what we do in parsing is we're based our algorithm off GLR parsing. That's generalized LR parsing, developed in around '85 at Carnegie Mellon by Tomita. It's okay if you don't know it. I'm going to explain how the parser sort of works in general terms so you guys can follow what the differences are between my algorithm and this original one. So in our parser, we've got a nested if statement here. And so we want to parse it. So the first thing we do is we lex everything, and we move our if keyword over into our parse. Then we take our predicate expression and move it into the parse. So moving things over to the left is moving things into the parse. Then we take our next if, we move it into the parse, our next predicate, and then we have foo. Now, if expression foo is actually a perfectly legitimate whole if statement, because I don't really need an else. But I don't really know yet which one I should pick. So in normal parsers, you pick one. You always say move the else into the closest if statement. But in the GLR parser, we don't have to make that choice. We can actually do something different. We can fork our parser into two possible paths. One of them says that if expression foo is a statement, and that this little statement is done, and the other one doesn't say that. So what I'll do is I'll continue both parses at the same time. And so I'll move else into both parses, and I'll move bar into both parses. And now at the top, I've got if expression foo else bar, so that's a statement too. And notice that's a different statement than the one on the bottom. Now if I complete the parse, I get a second statement up there, and I get a statement up there. There are two different parses for the same set of words. They both have the same yield, which is really important. And actually, in reality, these two parses are not, we don't fork threads. That would be crazy. We do a lot of structural sharing. We do a lot of sharing of the parse state itself. We do a lot of sharing of the parse, of the yield of the parse, of the tokens and the subtrees that make up the parse tree. You have a question?
You started describing stuff in the parsing layer, but there must have been a split that must have happened because of the homophones also, right? Right after lexically.
Yes, and I'll explain that. This is the algorithm that cannot support homophones. So in my next thing, I'll talk about the homophones. Yeah?
This if thing is inherently ambiguous, right?
Yes.
So both are valid.
Both are valid. That's fine. Yes. That's why it's ambiguous. So no, I don't mean to joke. It's a question in most programming languages. When you write your grammar, the analysis tool is going to tell you have, in this case, a reduce conflict, and you're supposed to have to fix that manually. And most people fix that by saying prefer the top solution, prefer the top parse tree, so that the bottom one never exists. So I was just giving an example just to show that there is an ambiguity. All right. So what's important with GLR is that whenever there's a structural ambiguity, the parser will fork and try out both possibilities, and in which case it actually can fork many times, depending on how much ambiguity there is. And what's also important to it is that that ambiguity is bounded locally, so that it does not fork excessively for long periods of time, and that eventually it does have the ability to merge back together into single parsers when the ambiguity is over. Whenever there's no ambiguity, it's order n in time, and whenever there is ambiguity, it's order n cubed. But it's always essentially order n squared space. So the thing that I did is I added the ability for the parser to fork when there's lexical ambiguity, when there are homophones on the input. So let me show you how that works. So we've got an example. If 55 is less than x, all right, so this is a sort of a partial if statement, just to get going, because it's pretty big. This is work that's published in LDTA last year. So first thing we do is we're going to lex our input word. So if is a keyword, and we'll move it into our parse, just like we did last time. Now we want to lex 55. Well, what is 55? 55 could be two words, 50 and 5, that are both identifiers. It could be 50 as a word and 5 as a number, or the opposite. They both could be numbers, or they could actually be a concatenated number. So lots of different interpretations just for one word. what we're going to do is we're going to, I'm going to move that into the parse. And actually, I'm going to show it as a replicated parse on the left. Notice actually on the right, our input stream is now mostly the same length, except this one, this input stream only has 2 tokens in it, not 3. So that's actually kind of important. You pay attention to that. So now what we do is we've got our identifiers in the input and some numbers. Well, after an identifier in spoken Java, you can kind of have a lot of punctuation. You can have an open paren or a dot. So let's replicate those parses, and we'll pretend that we inserted an open paren or a dot. And I'm replicating the bottom 2 parses twice each. OK, and now, of course, you've got to replicate the right side, the input. Again, we don't actually replicate anything. It's just for illustration purposes. So now what we want to do is we want to take our next layer of input and move it into the parse. But not everything is going to parse successfully, actually. So what happens at the top is you're saying if 50.5, and well, that's not really legal. You're not allowed to have a number after a dot if the thing that came before it is not a number. You can't have 2 tokens kind of separated by spaces in this language either. 2 numbers or identifiers followed by numbers. So we get rid of the gray parses. And what I'm going to do now is just I'm going to get rid of those and move everything else down. So let's pop those down to the bottom. So now I'm left with a bunch of parses. And again, you know, I have an identifier. So I can have open paren dot, or in this case now closed paren because I had an open paren before. So now I'll replicate it again, get a lot more parses. And I'll take my input token, which is the less than, except for the bottom one, which is, you know, x. I'll lex that, so everything's an operator except for the bottom. And then I'll move that into the parse. And of course, lots of them die again because you can't have 2 punctuation tokens kind of next to each other like that. So I'll get rid of those. By the way, this is Java 1.4, not 1.5. And pretend you don't need a paren at the beginning of the if. So we'll get rid of those. And then what we've got now is the ability to then lex our last input token. And notice the bottom one is already done. Doesn't have to keep going. And we move it into the parse. OK, and now let's show you sort of what the different parses might be. So I'll spread these out on the screen. And we'll go from the bottom up. The first one says, if 55 is less than x. That one's nice. That's an expression. If 50 paren 5 is less than x, that's not really done. So I'm just going to put those away for now. The next one above is if 50.5 is less than x, which is probably not something you would have expected. But since nobody says dot, it could have been. If 55 is less than x, well, if 50 is a method call and 5 is its argument, and it's perfectly legal, then that would be a great interpretation. And then finally, if 55, where 5 is a number and being passed into the method. So all these interpretations are actually pretty legitimate, except when we try to figure out which ones are legal.
You could have put a closing paren in one of the pink ones.
Yes.
And then you could have, you know, 50 being a function call, which takes in a Boolean.
Yes.
5 was the next. You didn't do that one?
Yes. Because if the example were to continue, that we
Oh,
do
okay,
that.
all right. Yeah, sure.
So notice the big thing here is all these parse trees now do not have the same yield. The bottom of the parse tree is not the same. And we've also been, you know, forking our parser based on all these sort of multiple homophones and missing punctuation. So the XGLR, that's what we call this algorithm, is a generalization of GLR that supports this kind of forking on lexical ambiguity as well as the structural ambiguity. What I kept mentioning about that whole the yield problem being very different across multiple parses, we actually do a lot of effort to make sure that you preserve the structural sharing that GLR has with the yield. Otherwise, you would get exponential space instead of n squared space in your parse. And also, notice that I told you before, the parses got out of sync. One parse finished earlier than the others. What's really important in this analysis mode is basically if one parse kind of gets ahead of the others when those parses kind of start. You don't want them replicating work that the one that got ahead of already did. So you need to be able to support parser merging, which is another feature of GLR, even despite the fact that those parsers might be out of sync. And so that's other challenges we had to face and fixed. We built Blender, which is a combined lexer and parser analysis parser generator. And actually this is sort of a key piece that you need to, in this work, combine the lexer and the parser generator together in order to understand these ambiguities, because a lot of what the parser does is direct the lexer to do particular things when there's an ambiguity, instead of just having a feed-forward system. So there's feedback from the parser to the lexer. An example of that is for, we can deal with embedded languages, such as like Bison, where you've got a regular expression followed by a code in C code. Now, the boundary between the regular expression and the C code, which is 2 different languages and 2 different lexical definitions, is white space. Sometimes it's an open brace. And often that means that the boundary between those 2 languages is ambiguous. So we might be lexing in 2 different languages at the same time, in which case the parser kind of needs to tell the lexer which language to lex in.
Just a quick question.
Yeah.
So how does this combined lexer parser fit into the rest of the pipeline? Is it the case that it produces a bunch of parse trees and then the semantic analysis that follows then rejects even more of them and tries to find one last one that will work?
Yes, and that's the next couple of slides.
Okay.
By the same token, you could argue that you want to have a blender that combines lexer, parser, and semantic analysis too.
So Blender is a generator, not the analysis itself. So there's a difference between, in language tools, there's a lexer parser generator which generates tables versus the runtime system which actually does the parsing and does the lexing. So the runtime system is actually very traditional. There's a lexer, there's a parser. Sometimes the parser kind of tells the lexer what to do, but not very often. And then all of those results are passed off to the separate semantic analysis. So they're still modular for the most part. The generator is just so that the parse states know more about what lexer state you're supposed to be in. Just a little genealogy for those who are interested. Tamita invented GLR based on some weird algorithm by Lang in the 70s. Farsi fixed it, Reckers implemented it. It moved off to the Netherlands where they went and decided to get rid of the lexer entirely and merge it into the GLR parser. In our group, Wagner made the algorithm incremental, which basically allowed it to be used in an interactive programming environment without performance problems. I went and extended for input stream ambiguities. And then Adrian Johnstone, this guy from Britain, who's funny, well, he thinks he's funny, he came up with a new formalism for like fixing the GLR parser that Tomita came up with the GLR algorithm that he kind of likes better, and then went off and started doing all sorts of weird parsing algorithms. But he's a cool guy. OK, anyway, we're up to the semantic disambiguation at this point. Is everyone kind of comfortable? Any more questions so far? OK, so here's an example of some Java code that loads a file from a stream. OK, and it's pretty generic. What I want to do is at the cursor point, I want to add file to load equals stream.readString. So I want to read the file name from the stream. And the code that it should produce when the person says this is file to load equals stream.readString. So that's our goal for this example. Okay, keep that goal in mind. Now, the question is, when I say file to load, even just those 3 words, I have so many different interpretations. I've got file where it's a variable. I've got file where it's a method. I can spell load in different ways. I've got file to load as a single word. I'm not showing you capitalization here, so there's actually more. This is just a few of the possibilities. So now how do I figure out which ones are the right ones? Because that's actually pretty important. So what we do is we actually built an incremental semantic analysis system, because I like to build things. And it's able to answer questions of the form, what does this name mean, and what names are visible here? Or what I like to say is, what can I say here? Because that's really useful information for constraining the domain of the speech recognition, for getting more accurate speech recognition. Now, what we built is an extension of the visibility graph, which is a data structure for names, scopes, and bindings that was developed by one of my advisor's graduate students in the 80s. And I'm the first person to find a use for it, which is very cool. Essentially, it's incrementally updated over time so that it doesn't take a long time to generate, because we kind of do analysis after every word that comes in. And we also had to extend it so it actually worked for name propagation and for incrementally updating. We use this for type checking. Now, the biggest advantage of this visibility graph is going to be order 1 lookups on names, and I'll show you how that works in a second. But again, we could say, doesn't Visual Studio do this? I have to customize that for the audience. Doesn't Visual Studio do all this name analysis? Don't we have code sense? Can't you already look up what the words are? And the really key thing is I can do it faster for my domain, which is being able to do this after every word. Now, what we have is we have a graph, and this is a really simplified graph of our example, we have 2 scope nodes in the graph, one for the class and one for the method, and each one has a set of bindings in it which say what are all the names that are visible or defined in this scope. So the first one says in the class I have a method named load. In the method I have 2 variables, one's a file to load, which is a string, and one is a stream, which is an input stream. Now, there's a little bit of propagation, so we take the binding from the first node and push it down into the second node, and this is an arbitrary graph, so we do a whole big propagation step to push everything into these nodes, and what you get by pushing all the variables into a node is an order 1 lookup on a name, because whenever 2 names clash, we basically pick one that, according to the language semantics, is the one that would have won anyway, based on the name inheritance rules of the language. So with our order 1 lookup, we can now answer all these questions, like, is file a visible variable name? Well, so I'm looking up these guys. Is file a visible variable name? I don't see it anywhere. I'm looking up in this scope here. So no, so that means those are not the right possibilities. Is file a visible method name? Again, I don't see it, so no, it's not. So that one goes away. Is file a visible method? Is file to load a visible method name? Well, file to load is visible, but it's a local variable. So that's not the right answer. And the last one actually is file to load is a local variable. So that's the one I would pick. So that's how I get rid of all the others. Yeah?
So is this a return to the battle days of structured editing where I have to do everything in order that the programming language wants? So for example, I can't use a variable before I declare it because then it won't get recognized then.
So I'll give you a half answer, half yes, half no. Some of it is a return to structure editor just because it's for 2 reasons. 1, it's a dissertation, so it's easier. And 2, you don't really have a cursor when you're programming by voice because you're not just speaking code in a row. It's harder to do that, to make a completely modeless voice-based editor. The other answer is no, it's not a structure-based editor. It doesn't have the flaw where you have to program in a top-down way because if we can't disambiguate, next slide, what we do is we basically leave the ambiguity around. If we disambiguate incorrectly, we leave the ambiguity around. You still can see one interpretation, but if let's say we resolved an ambiguity as we said foo bar, and foo is foo.bar or foo method call with bar as an argument. And let's say I intended it to be the method call, but I haven't defined the method yet. But there is a field named foo, and it does have a bar subfield that's legitimate. So there should be 2 legitimate answers, but I only saw one, as the analysis engine only saw one, so it resolved it. Well, it resolved it, but if you don't touch it, and then you add your second method name foo, it will it'll re-ambiguate, essentially, foo bar, back into its 2 possibilities, because those are now 2 things that are legal. Okay. Now, you just have to train the user not to touch it when they see that it's wrong. That's part of the training. But let me get to that, because the training comes next. If the user types at it with a keyboard, we assume that that's unambiguous, and he really means what he says. So if he fixes foo.bar into foo paren bar, close paren, then he wins, and all the ambiguity there goes away.
So as I understand it, though, if you don't have a foo or a bar in your environment, then you could have multiple.
Yes.
Then you could have ambiguity, and then you could go resolve it later. So you could first you could first do the use, and you could later go do the definition, and that definition could resolve the ambiguity.
Exactly.
So that's quite different than structured editing, where if you do a use without a definition, it just complains and it doesn't even let you put anything in.
That was partly why I gave you that half answer.
Okay.
But then you can't really throw away those parts.
No, we don't.
Right.
But in the previous slide, it just showed, it's just
pretty
thrown
much
away, right? So you can't really throw it away.
What happens is basically we have a data structure called an ambiguity node that has all the possible parsers underneath and knows which one is the currently selected parse. And we visualize that.
Cover all the others.
Yeah. They can change it at any time as the user decides to pick or needs to change our minds.
So you're using a lot of space, right? I mean, it's fine. I like this stuff.
Yeah.
Okay.
So the space issue is an important thing, and we address that with the user interface. And I'll talk about that in a sec. So we do have some ambiguities that are not resolvable, such as print line or this nested if statement, where you don't really want to decide for the user what the semantics are. So we just leave those alone. If the ambiguities do remain, what we do is we allow the user to kind of pick And that's based on some of the ambiguity mediation stuff from Jim Mankoff. So I want to do navigation and editing, though we're kind of running short on time, so I might skip a few things, but we'll be okay. I did another study in one of the classes I took on how people navigate using voice recognition tools. And what I had them do, I didn't want them to just use the find tool to look for a word, because it's kind of bogus. What I wanted them to do is to look for something they didn't really know exactly what they were looking for, but they'd know it when they saw it, which is a lot of times very similar to what you're doing with coding. You don't exactly know what you're looking for, but you'll recognize it. So what I did is I took Romeo and Juliet, and I said, look for the place where Romeo cries out after killing Tybalt, in Act 2, Scene 1, or Scene 3, or something like that. So you can't really search for Romeo, because he talks a lot. And you can't really search for where Tybalt stops talking, because that's not something search tools usually give you. So you kind of have to scroll through. And using the speech recognition commands of go down 5 lines, go down 10 lines, go down 20 lines, keep going, page down, page down. And of course, most speech recognizers force you to pause in between you saying 2 commands in a row, page down, page down. It's very slow, so we tried to come up with a better way that wasn't always better, but we learned something. So we said, how long does it take to do this? How many commands have to come out of your mouth to make this happen? How often, because you're saying these commands, does the system get it wrong? Now, what we did find is the cognitive load of searching is incredibly high. What you're usually doing is reading at the same time as when you're trying to control a system. What we had is an auto-scrolling system, which was worse. It basically scrolled at a certain velocity, and then you can control it with saying faster and slower. It turned out that humans can't read unless the text is stopped. So we came up with a scroll and stop system, which then you control the length of the pause. But the problem is that voice recognition has a huge delay. It's about a 1-second delay between the time you say something and the time it reacts to you. So if you're going through at any fast enough speed to sort of see something, read it, and spot it, and then say stop, by the time you said stop, it's already gone like 4 pages ahead. So it's like your TiVo. When you press fast forward, it goes ahead, and then when you press play, it jumps back a little bit. Now, they figured out how to get that exact, because I'm impressed for the most part. I can't do the 3 fast forwards. I can only do 2. It takes a Jedi Master to get the 3 one correct. In our system, we didn't have any timing information of when the voice actually came into the microphone, so we couldn't even do this at all usefully. We found there were a lot of commands that people had to say. There were too many errors, and we decided, you really do need to customize your voice recognition commands for the environment in which you're working. So what we did is we built some navigation and editing commands to make our system a little bit more usable. Now, first I could describe shorthand editing, which is from JJ over there in the corner. Is our undergraduate. He came up with this idea as a freshman, and he joined our group and implemented it with Harmonia. Shorthand editing is a way of essentially doing a structural kind of edit on your tree. So what you get is a structural cursor that you can move around the tree by saying like down and up and down and left and right. Then what you could do is once you're editing, once you're kind of on a particular word, you can say things like protected or private. And it will basically replace the words that are correct with the other possibilities for what things could be put into that statement. If I said static, that would have actually added a word, not just replaced the word that I was currently looking at. Now, in addition to being able to just edit, I could also move down. And let's say I wanted to take that line and move it down to the next line, just kind of swap it with the one below it. So I would say like push down. And that essentially takes that line and moves it down the screen. So it's a little bit more, it's cognizant of structure in your program. It's cognizant of the statements, of the words. And what it can do is basically allow you to operate on larger entities than just characters, which is something really nice for programs. Now, in addition, saying down, 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 down is really long, especially if you're kind of scrolling through your document. So I came up with a faster way of doing sort of really quick navigation, which is called context-sensitive mouse grid. What you do is we number all the classes that come up on the screen when you say mouse grid. So we've got numbers there. And then all you have to do is read the number off for where it's pointing. And you say 1, 1, 3, select. And it hierarchically navigates into your code and then selects a line that you perhaps want to edit. So I'll say edit. And what it'll do is it'll take this code, turn it into spoken Java from Java. So which is on the bottom there, file to load equals quote file.text quote. Whenever we translate it from Java to spoken Java, we add all the punctuation in. just because it's easier to read. And then
You mean you display it?
we display it with the punctuation.
Okay.
So in which, punctuation has got to be there in Java anyway. So then the person might say file to load equals stream.readString and put it back. And because we know where it's going, we know how to analyze it in context, and we use the context of the program to figure out which one's the legal interpretation, and which is what we have there. So that's how the whole system generally works.
So, for example, if I had to, let's say there was a complex expression, I made a mistake, instead of plus I typed times.
Yes.
And all I want to do is just replace the plus with times. Then I would read the whole thing and say, repeat it with times instead of plus.
So two answers. One, you can edit structures as small as you want. So if it was 5 times 6 or 5 plus 6, you could get down to the 5 plus 6 and only have to say that part again. You can't just say the operator right now. And the other thing is when you restate it, it's bringing down the original text into your editor, and at that point you're using kind of your normal voice recognition tools for playing with that, which allows you to actually select that star and edit it and change it to a plus as text. Now, the key thing about this user interface that's nice is that it fixes our ambiguity problem, our ambiguity blow-up problem. So you say lots of words in a row, let's say, 50 words or so, and you get like 5 bazillion ambiguities. That's obviously a problem for any analysis system, but if I only let you type into a one-line thing that's only this big, you can't fit that many words in there. So you can't overwhelm the system with too many things to say. And in which case, you probably don't want to be saying way too many things anyway, just because you want to see the results of what's happening as you edit. Now, this is sort of an ed-style editor. This is like very retro. It's tractable for a dissertation. If you were making this like kind of robust and power-hungry, you'd make this more like VI or Emacs or something, or something perhaps even better.
Actually, I was going to say this reminds me of VI because there's this navigation mode and then there's this text entry mode, right? So the thing that people always hated about VI is there was no visible indication as to which mode you were in. So is the yellow highlighter here or something my indicator in the UI as to what mode I'm in?
Well, the yellow highlighter is the navigation cursor. When you edit it, you do get a little like kind of text box on the bottom, which is where you're currently typing. So you're not really, it's actually really more like ed, because in VI, once you say I for insert, you can actually do any text editing on that line. This actually is much more constrained, where you're editing structures and only being able to type that particular structure.
How do you recover from recognition errors?
The recognition error recovery is something that we just use the stuff that comes from the Dragon. So it's actually a training problem, which I'll get to in the next step. So our study, we're doing a study to see how people use this next month, and we want to train programmers on speed. And one of the things that you have to train them for is when the system makes a recognition, when the system appears to have made a recognition mistake, there's a class of mistakes that are real mistakes, and then there's a class of mistakes which are things like that the system just doesn't have enough information to resolve an ambiguity, or perhaps resolved it wrong because of a use-def ordering problem. Those are kind of, or perhaps spelled something wrong, but spelled it consistently. So it would still compile, but maybe they said for I equals 1 to 10, and it used EYE, and they really want I. And the system at that point, we need to train developers not to touch it, because it'll eventually get it right. And it's similar to what you have to do to train people for normal speech recognition, is that you can use speech recognition to dictate a document. You could just start dictating and watch the words come up on the screen, but it tends to slow you down a lot. And every time you see an error, you want to fix it right away, which also makes you forget about what you were going to say, because usually that stops you too much. It interrupts you. And successful speech recognizer users don't look when they're saying something, and they dictate like a whole sentence or a whole paragraph before they look and try to correct the 1 or 2 mistakes. The same thing I think is going to be true for this programming project, except on a larger granularity. You want to be able to say more of your program, and then only before you want to compile it do you want to then fix the errors. And maybe there's a trade-off in time there. That's something we'll have to look at when we actually start training people to use this.
So when there are multiple possible parsers when it is ambiguous, is there any visual indication, or is there any way that you can sort of cycle through them to?
Exactly, yeah. Annotation, underline, little squiggly in a certain color, and then you can click on it to get a pop-up window, a pop-up menu to show all the possible interpretations and pick one. That's JJ's going to do this summer. Okay, so our training is basically build some new code, like a data structure. That's something that even novice programmers should be able to do after their first computer science class, and write some algorithms that go along with it, like reversing a linked list. And then we want to test also editing. So I want to see how it works for authoring, where you don't have a lot of context, and for editing, where you do. Now, things we're looking at are, of course, speed, because everybody wants to know how fast or slow you go. The kind of mistakes that you make when you forget what you can say, or you forget how to say something, like how non-intuitive is the language, despite having done a user study. So this is the kind of things we want to iterate over. Also, metrics on how often does it figure out where the word boundaries are incorrectly. How often does it disambiguate incorrectly, and how often do you get these irresolvable ambiguities, where you get like these nested if statements where you don't really know exactly what to do. If that happens all the time, this is going to be a completely unworkable system. I'm not sure. It's going to have to, that's why we're doing the study. Now, finally, I just want to sort of sum up and tell you sort of what I did again, just to remind you. So first, we do a study of programmers. We figured out what they would say if they could speak code out loud. And then we design an interactive editor that will support this kind of spoken input form. So we designed a spoken language, and we designed the analyses, extended a lot of compiler analyses to understand the spoken language, which is very similar to programming languages, and then are able to analyze this form and put it into the editor. And we designed some user interface techniques to go along with it. Then we evaluate our design, or we'll be evaluating next month, our design and the tools for using the system. So before I go to that, does anybody have any questions now on the programming by voice stuff? Yes?
So, usually when you program, you don't know exactly what will be your program, final program, basically. So you modify your design or your code along the way. And you will pause, you will have some spontaneous feature of this spoken language. So, and you also want to think, sometimes you want to choose the intelligence to know what you can say actually. So how are those kind of issues handled in your system?
So it's similar to the discussion that I had with Rob about whether this is a structure editor or not. Structure editors are very prescriptive in the way that they require you to code in a particular way, top down, and know what you're coding before you code it, know what all the functions are going to be called, or what function you need. Our system is a lot more free-form. We're based on some technology that allows you to have erroneous and incomplete programs still be analyzable. So you could program in kind of pretty much anywhere you want. Our system might find it more troubling to analyze something without any context because of all the ambiguities that might be there. But you can still choose to disambiguate them yourself. And the pausing and other stuff, why don't we get to that after the talk? Yeah?
White space and comments, things in the program that's being entered.
So white space is, we kind of pretty print the program if you're saying it by voice. And comments come when you, we can just turn on normal dictation support from the program, from the speech recognizer, to be able to say, you say comment, and then you can just talk for a while. All right. So let's get to sort of future work. Where could this go were someone to continue working on programming by voice? And not to say I'm, potentially not working on it, but, I'm bitter. But I like my stuff. So, OK. The first thing we could do is look at semantic disambiguation. A lot of what I do is pretty much just take all the different ambiguities and type check each one and say which one is correct. Now, I think you could use some ideas from machine learning and from natural language processing, like there's stuff that they tried to do in the 60s for English, and adapt it, maybe adapt it for disambiguation of programming languages where you do have the complete semantic domain. The other thing I want to do is to try to learn a little bit about how you program. Because if you always say for int I equals 0, and that always is a for loop, there should be no ambiguity there. So if the system can learn from the user, then it can help do that. The other thing is we do a feed-forward system of ambiguification, if that's a word. And that leads to quite a few ambiguities that make it to semantic analysis that are required to be interpreted, which is why I have to cut down on the size of the input. But you could imagine taking information about the program you already have, like semantic analysis, and passing it along to the lexer and saying, well, foo bar moo is not an identifier in my program, so that unless you had just said the word declare and you're trying to declare a new variable, this is not likely to be the right one. So you can get rid of some ambiguities early. The other thing I want to look at is sort of higher level linguistic programming tools. What we found from when people were speaking their code is some people talked about their code and not just said the code out loud. And some people talked about it in a cool way. So if the code said foo.a equals 0, foo.b equals 0, foo.c equals 0, 2 people said set all the fields of foo to 0, which is cool because that's shorter. And that means that if you can support that kind of slightly higher level discourse, you could actually make the programmer a little bit more productive, especially in the voice world where they're probably going to be a lot slower than a typist using this system. Also, phonetic search. One of the problems with the find dialog when you're using the voice is when you say, like, find foobar, and it spells it wrong, and you're like, scratch that, and it writes out scratch that. And then you say, no, correct that, and it writes out correct that. And you're like, no, fix the spelling. And then it says, how do you want to spell scratch? And you're like, no. And a lot of people cancel the find dialog and start over again whenever they make an error. So you get a lot of cascaded errors. If find were phonetic, then sure, you'd find more things, but that's conservative. At least you could do is just find a whole bunch of things, and then you'll pick which one is right. Also, the audible feedback is going to help a lot with training, because you'll be able to highlight something and say, how do you say this? Now, you could also look into supporting other types of tasks by voice, debugging, the rest of the IDE. Commenting by voice is kind of neat for, if you imagine, for a code review. I could just get your copy of code, talk about it, and then I don't actually have to meet with you. Well, unless I want feedback and all. But at least you could do is they're contextualized, so you just kind of embed it, kind of like a tablet PC journal program. You could also design spoken variants of lots of other programming languages like C, C++, C#, other types of design languages, some robotics languages, maybe some SQL. This could revolutionize the idea of programming, code based on voice. Anyway, no, it probably won't. Okay, so where might I go? Yes?
I don't understand the differences between Java and JavaSpeak.
Oh, so JavaSpeak is output. It's when you say the code out loud only. It was developed for blind programmers to sort of be able to have them understand what the code that is that they're writing by speaking it back to them.
What is the construct which is there in Java, which is not there in JavaSpeak or vice versa?
So let me take that offline, because I think there might be a mismatch between spoken Java, and JavaSpeak, and I might be answering the wrong question. So, okay, thanks. So where I might want to go is I really think there's a rich interaction history that happens between the programmer and the development environment. And there's absolutely no reason why that should not be captured and used to help the programmer. Such as, let's say, I don't know, I was editing some code and I checked in a week later, and now I don't remember what I did. Because I fixed at least a few things. But if you knew what the programmer had been doing, maybe he'd been editing a function, maybe he'd been adding a field, maybe he'd been fixing bug number 42. You could start grepping all that information and start grepping through the bug database and start looking through the email documents and figure out, oh, maybe you were fixing this bug. Did you fix this bug? And help write the CVS message for the developer. You could also do task inference and start figuring out, instead of having low-level keyboard data, you kind of want to figure out, what does that mean? What was the developer really trying to do? Because then you could build tools that help them with the tasks that they're trying to do. And also coding guides, if there's a certain way that people in your organization code, there's a certain style that they have. Maybe you want to learn from somebody who's expert and you're a new guy on the team. You want to somehow take advantage of the fact that you want to kind of data mine his programming stream and say, well, every time he calls a function, he always checks the H result. Well, maybe when I code, I should always check the H result too. So in addition, I also want to look at non-code programming communication. Like when I'm talking to you in the room with the whiteboard at the end of the hall in the lounge, and we're talking about the code, maybe we have the code in front of us, maybe we don't. How do we know that we're talking about the same things? How do we express ourselves? How does the programmer talk about code? It's kind of a natural extension of talking code itself. But there's no, I think there's pretty much no related work in this area. There's a lot of work on programmer comprehension. Here's a page of code, tell me what it means. But there's very little work in saying, how do you talk about this piece of code? So I want to learn a lot about that. That could also help you with capturing design history for long-lived pieces of code, code that lasts, that expands a lot of different developers, code that's really big. If I am a new person coming onto a project, how do I know where to start? Well, usually I'll go and ask somebody who's smart, who already worked on this code for a long time. But what if that guy is in Nepal? What if he's on vacation, or what if he's left the company? What if he's moved on? I don't have the right resources. And even when I do get the right resources, they just tell me stuff and I just keep it. So there's no capture of this kind of knowledge about the program. And that's something you really do, I kind of want to fix. Now, another weird project is I call programming in the large. So what does it mean if you could have a whiteboard to program on? Like, a lot of my friends take their code, they print the entire thing out on paper, and they spread it out on the floor. And they say, okay, well, this function calls this function over here, and this one calls this one, and now I understand what my code is doing. Well, I wanted to look at visualizations that could take advantage of a lot of that space. If you have very large programs, you need a very large space to look at it without anything really clever. Now, also, sort of a pet peeve of mine has always been, I never know what my compiler is doing. If I'm a scientific programmer, I'm compiling code and I really care what the optimizer, that it unrolls this loop 4 times, that it assigns this variable into a register, and that this code I really think is dead, but I need to have it in my code. Well, how do I find that out? If I'm a compiler hacker, I go and look at the assembly code, and then I say, okay, well, I know this assembly code backmaps to this source code, and let me figure out what it does. And then if I tweak the source code a little bit, I can make the compiler unroll it one more time. That's lame, especially for people who, most programmers haven't taken a compiler class. Especially domain experts like scientific programmers really haven't taken compiler classes. They haven't taken programming classes. So they don't really have a hope of this. What I want to do is try to visualize some of these optimizer results, some of these program analysis results in the editor itself, and show the user like a representation of their code that says, look, it's unrolled 4 times because you can actually see it 4 times in a row. Or highlight dead code in gray that says, oh, this code looks dead, and just show that as they're editing so that they are aware of what's going on. This also has to be scalable, and that's actually really important because your programs are big. Most programs are 100,000 million lines of code, and control flow graphs and parse trees and things like that, they're just completely useless unless you know both what you're going to do with them and also you find some way of filtering out the information to just the stuff that you care about. Yeah?
What is the maximum length of the code by number of lines or number of characters which you have written in your tool?
In my tool that I can handle?
No, not you can handle. What is the largest program you have written? What is the length of the program that you have written using your tool?
Oh, written using my tool.
I'm wondering, is it possible? I mean, what are the effects if I use this tool for 2 months on my programmer productivity?
I don't know that yet.
So what are the class of programs which you have written using this tool?
I've only written really small programs.
100
because, oh yeah, like 50, 20 lines. Just to test it, Sort of getting to the point where it's trying to be ended, so I'm getting it to work. More about fixing bugs at this point than trying it out. That's what I want to do, the tests, the user tests. Another project I want to do is sort of looking at scalable debugging. How do you debug concurrent applications when you have lots of threads? Because I certainly do not appreciate putting up 15 GDB windows and typing next, and printing out 15 different variables 15 times, or even just seeing a big gigantic array of variables, because if I have a program that's running on 8,000 processors, there's no way I can understand that. I need a statistical debugging thing. I need to be able to ask distributed queries. I need to be able to say things like, breakpoint when 3 processors have different values for this variable. That's not something you can easily say in a command line debugger or even something like Visual Studio Debugger. But it's something that's really important when you have these large programs. Even concurrent applications of just like a couple threads are still get annoying to debug. And so that's something I think would be really interesting to look at. So that's it. That's over. And you can ask me any questions you want. I could leave this on the screen if that's interesting for you.
Can you show us some programs which you have written using your tool?
No, I can't, not right here. The tool only works on my computer in my office because of licensing issues and because it's the only fast PC I have. It works on Windows only right now, unfortunately. It used to run on my Mac. And then it used to run on Linux. but it keeps, desktop speech recognition is kind of dead. So all the vendors keep taking away their tools. It's very frustrating. Means I have to finish really fast.
What is it? Desktop speech recognition?
Yeah.
What does that mean?
Speech recognition for desktop users, for people who use like a dictation. I don't know. The thing that's really winning is speech recognition for telephony.
For what?
Telephony. So if you call up United Airlines and you say, I want a flight from Zimbabwe to Harar, well, I guess it's the same country, but yeah. But that kind of thing, being able to understand that is where all the research is going.
Why is that?
Why? Lots of money. You save money when you don't have operators, when you don't have human operators handling phone calls.
No, well, why is speech recognition on the desktop?
Oh, why is it dead? Because it was a little overhyped. So the problems are that it's really difficult to control your computer by talking about it. It's really difficult to replace a mouse by verbal communication. So being able to point at something, like if you were to, here, tell me where this is, using your voice. It's a couple inches over from here, it's a couple inches up. Humans are really bad at estimating distance. So it taps into everything that humans are bad at.
So why do you think this is going to succeed?
Because I'm actually looking at how, so two things. One, I'm tackling a population for which there's not many other choices. So it's sort of more compelling for that reason. And it's also something where I'm trying to look at how they might use it more effectively to improve upon generic use of voice recognition for the desktop and say, customized explicitly for programming, how do we adapt this tool and provide tools that really are specific for the problems that programmers are going to have.
How do you use your voice? You just use their general detection model?
I use their detection. I have trained their model. So they have a language model which is sort of based on English language documents. What I do is I take a corpus of Java documents that usually are they would be from the program that the user is writing. Take that, translate it to spoken Java, and sort of continue training the speech recognizer so that it's able to handle things like saying import Java lang system, and those words can come in a row. So that way it at least starts giving you the right words.
Most of your commercial recognizers can handle, in addition to this kind of dictation language model, also something that is like context-free grammar.
No, not context-free. It's a finite state machine written as a grammar.
Right, but the bottom line is you can express any BNF expressible grammar that the recognizer can take it and actually performs better.
Mm-hmm.
So you're talking about putting a lot of context and back to the lexical recognizer, lexical analyzer. Why don't you just push it all the way to speech recognizer and see what happens?
So the speech recognizer can't handle recursive grammars. And there is no programming language in existence that's not recursive.
But you are not saying it in recursive, right?
No, I am. Actually, most of what you say in a programming context, even with a short statement, is highly recursive. Like, x gets 6. X itself is an expression, gets 6. I can have like a statement instead of just 6. I can say x gets, call this function. And that usually loops back on the same kind of expression.
But the lexical expression itself is not.
The lecture doesn't know about much of this at all. It's the parser that has to know about all the analysis. So you can't really push it all the way back into the speech recognizer because the parser is really the one that's the most powerful one to figure out what the context is.
But if that is the case, I mean, you only need a left recursive grammar, and a speech recognizer handles that.
Okay, we'll talk about this later, but they're generally limited to finite state machine grammars.
Okay.
Yeah.
So modern programming editors like Eclipse or Visual Studio, they have these neat features like, pop up, what's the next method you want to type here, things like that. So have you thought about how that integrates into this kind of work? Because, I mean, that makes typing much faster already. Mm-hmm. So does it speed up voice by voice programming as well?
So in this particular way of doing things where you're it's a very modal editor. You're editing a structure at a time. There's no opportunity for analysis while you're talking. So there's no way to do the code assist, which is the thing that pops up the other things. Now, one of the reasons, I think there's two reasons for code assist. One of the reasons is because you don't want to type out what you already know you want. And the other reason is that you don't know what you want and that you're kind of just scrolling through. And in the case where you don't know what you want, it's going to be that there's no help. You're right. That's something that could be done with the next generation of this, where you actually start analyzing as you're talking, instead of analyzing complete structures. Good idea. Hard. So there's a lot of predictive parsing that would have to go on.
Right.
And I tried to do a slight side project on that at one point.
Couldn't you just leave a little cookie behind? Couldn't I say something like, if x.IntelliSense, +3 is less than 10, and then after you've parsed it, you know that IntelliSense is a place where I want you to go and pop up the choices.
That's interesting. Okay. It's an interesting idea. I have to test it out. See how that works. Any other questions?
You know how they say that we want to enable grandmothers to program?
Okay, yeah, I've heard that.
I thought it was all bullshit, but I wonder if you enable programming by voice, you could actually enable, grandmothers to program.
Enabling programming by voice doesn't mean the semantics of programming are going to get any easier. And the language is still hard too. I mean, even, it's still like you still have to know what you're doing. I think there's a whole brand of research on end-user programming and programming for grandma, and programming specifically using programming without computers. Like you go to Intel Seattle Lab, who are working on that kind of stuff, like context-aware home and stuff, which is sort of non-textual programming. It doesn't need to be on the desktop. All right, well, thanks very much.
Thank you. So, Shaz, does your grandma want to?